Okay, so let's start. But for today's lecture, Carl is going to finish up the Nsight compute, and then he will continue into Nsight system. And after we finish all the profiling topic, I'm going to take over and talk about special hardware and acceleration and for deep learning. So Carl, take over.
All right. So we had just ended last time talking about some kernel level metrics and how to interpret some of those. If you'll recall, we were talking about things like memory utilization and throughput and things like that. And so that's all something that applies at the level of a kernel, particularly when folks are writing scientific codes or many other codes by hand. Sometimes the kernels can be quite long, have multiple different phases or steps, and it can be difficult to, based on just those kernel level metrics, figure out what the performance characteristics are of the different parts of the kernel. So the sort of final and one of the, I think, the most useful things about Nsight Compute is that you can look at the instruction level effect of a lot of different performance metrics. And so this is just a different page in the Nsight Compute GUI. So instead of looking at the details, we want to look at something, the page called the source. And typically, at least in my experience, what you're going to want to do often is look at it side by side, the source code, so the code that you wrote, and something called the PTX. This is sort of similar to x86 assembly. It's sort of a higher level assembly code that the driver will then compile to assembly that targets a specific GPU. But often, unless you're looking at some really specific, GPU architecture implementation detail, you don't need to know exactly precisely what instructions the GPU is executing. You can just look at this sort of higher level assembly, which is still very, very low level. So, it reduces everything to simple load and add instructions and things like that. And you can get some performance about each of these individual instructions. And if you'll recall that line info flag I talked about yesterday at the beginning, so this is really where that comes into play. So that is what gives this Nsight compute tool the ability to say these particular PTX instructions came from this particular source code instruction that you wrote, or source code line that you wrote. One sort of wrinkle in this is that you can write a single line of source code, especially in C or C++, that's arbitrarily long because the language is delimited by semicolons and not new lines. And these lines of source code can do a great many things internally. And so I've found sometimes in practice, so for example, if we're trying to increment all the values of an array here in this particular example, so this is going to be a load into a register, an addition into that register, and a store. So it's going to be at least 3 assembly instructions, probably a few more to compute whatever I is. So it can often be helpful to take some of these compound source code lines and break them up into multiple lines. That will allow there to be a more fine-grained correlation between the PTX and the source code lines. Right, because if I look at the performance of one line of source code, it might say there's a bunch of loads and a bunch of stores, but it's not necessarily clear always what in that particular line created those loads and stores. And so this is a simple example where it'd probably be easy to tease apart where the loads and stores were coming from. But you could imagine that there could be some register spilling or something like that. So you could have memory activity that you don't even explicitly specify in your code, sort of any number of complicated things, especially at high optimization levels. So I mean, when you sort of release your code, it might make sense to put it into a more compact, readable, maintainable form. But while you're going through and profiling, sometimes making these minor adjustments for profilability can be helpful. So one other wrinkle that comes up here is when you're profiling on a remote system, the correspondence between the assembly code and your source file can be lost when you move the profile data to the client system that you're actually running. But there's a way to fix this problem. As long as you have a copy of the source file on your own computer, you can just hit this resolve button if the source doesn't show up in this view and navigate through the browser to the location of the right source file and load it up, and then Nsight Compute will be able to reestablish the correspondence. So this will happen if the source file path is different on your client machine than on the test machine, or the development target, which it almost certainly is. So this basically works through something called instruction sampling, and at a high level, how instruction sampling works is basically every so often the position of the program counter is recorded, right? So in newer GPUs, every single thread has an independent program counter, and every so often we're just going to say, stop everything, where is everyone's program counter at? And the more often that we're in slower instructions, and the slower an instruction is, the more likely we are to sample the program counter at that time, right? So if we have a bunch of fast instructions and one slow instruction, if we take a random sample, it's proportionally more likely to occur during the slow instruction. And so we can use this to tell us which instructions are essentially executing more quickly and which are executing more slowly. So sort of at a high level, it's pretty straightforward. There's a great deal of other information that's also recorded to go along with this, but this is sort of how we tell what parts of the code are fast and what parts are slow. And so you may recall that we talked about the stall reasons, right? So there are reasons that every single warp instruction is not being executed. And so that could be it's waiting at a barrier, or there were just too many warps ready to go, or it was waiting for data, or something like that. And so the columns, when we record the sampling data, we also record which state the instruction was in at each of those sampling points. So basically, the more sampling data that a particular source code line has associated with it, the slower that line is. And then within that line, if you mouse over that, you'll be able to see a breakdown of why the warps were stalled during the execution of that line. So the other thing I'm highlighting on this slide is, sorry, let me take it back from the top. On the left side is the source code, and on the right side is the assembly code that was created from it. And so on the very left, you can see this. This is just a screenshot. On the very left, you can see the source code. Then there's a section sort of in the middle on the left where there's these columns of different data. And so these are the metrics that are associated with each line of code. And then you have the corresponding PTX and the metrics broken down by that PTX instead of by the source code line. And so the other thing that I'm showing here is if you click on a source code line, it will highlight on the right-hand side all of the assembly that was generated because of that source code line. And so you can see that this single source code line has a lot of different instructions with a lot of different performance characteristics in it. And furthermore, something that's very common in this compiled GPU code is that some of these loops will be unrolled. So this loop body that loads two values from our matrices and adds them into accumulator will actually show up several times on the right-hand side. And so that's just kind of another thing to pay attention to. Sometimes these lines of code will generate a huge number of lines of assembly. But basically, you can look at each of these lines and see why the code is stalled on each of these lines, and a variety of other metrics about it. And so when you're really drilling down into your kernel, trying to figure out why it's not as fast as you expected, this is really sort of one of the most fundamental and useful tools for this. Like I said, you can also look at the what's called the SASS instead of the PTX, but it's largely similar. PTX is much more well documented on NVIDIA's website, so sometimes it can be, even though the PTX is a little bit less specific, it can actually be easier to understand what's going on sometimes by looking at the PTX, because if you don't know it, it's easy to just look up in NVIDIA's PTX ISA specification. So you can see all kinds of things here. Yeah.
Carl, it may be useful to explain the SASS, for students who are not familiar with the portable kind of a code versus the assembly code.
Sure, right. So Really, the reason that there's this distinction between PTX and SASS is NVIDIA wanted to make it so that the GPU code that I compile today is forward compatible. So when they release a new GPU architecture, they don't want me to have to recompile all of my binaries. One way to do this is sort of the CPU x86 method approach, which is basically that, you know, when we compile a binary that's meant for multiple CPUs, we compile it to sort of a minimum standard of x86. And if any CPU that Intel or AMD releases has to maintain that x86 ISA. NVIDIA's taken a slightly different approach, which is they compile to this thing called PTX, and then at runtime, depending on the target GPU, the NVIDIA driver will compile it down to the actual assembly instructions that that GPU can execute. So this allows NVIDIA to be a little more flexible in the specific instructions and the specific architectural features on each GPU and make a few more changes between generations without breaking people's code when it's compiled. So we don't have to recompile our code every time a new GPU is released. The driver will take care of that for us. Of course, it's possible if you want to do various things to short circuit this process, generate specific code ahead of time so that you don't have to have the compiler do it, or you don't have to have the driver do it at runtime, and so on and so forth. But in general, that's the picture. So we have this sort of intermediate PTX representation, and then at runtime, that's turned into this SASS, which the GPU actually executes. Yeah, good question. So that's kind of the quick overview of Nsight Compute. You know, these things seem relatively straightforward when you look at them in a set of slides, and then once you start using it, you see that there's a whole number of possibilities open to you. So if you have the opportunity, I'd really recommend you try at least downloading the examples and running it through and clicking around in the interface. But I hope this has kind of given you a flavor for what is possible to understand about your kernel's compute performance.
Carl, did we ever get the right axis working for 498?
No, we did not. So there's a system called Rye that was developed by Professor Hu's group that I believe your homeworks or labs, I'm not exactly sure what they qualify
Number
as.
2.
Yeah, are using sort of under the hood. And we were talking a bit with the teaching staff about creating something where you guys could get a hold of some of these profiles for specific code and use them yourselves. But we never managed to do that. One thing I could do is create some profiles. I could run this through Rye and post the profile data and the source files, and then folks who were interested could download it and install Nsight on their own systems and open them up if they were curious.
Yeah, that may be a good idea. So that
Okay.
we can work with Xiaofan to make the output available to the class.
Yeah, so I can definitely do that. Sure, that sounds fine. And so basically, I can probably I'll figure out the right way to do that this afternoon, and we can let everyone know. Okay, great. So then the final step here that I mentioned at the beginning is once we understand there's not just the kernel performance that we care about when we're thinking about the GPU, we're also caring about how effectively the GPU is utilized by the entire system. And so instead of lumping these two tools together, NVIDIA has broken them into two different tools. So Nsight Compute and Nsight Systems is to look at how the system performance affects the GPUs. Nsight System can tell you a lot about what the CPU is doing. It even has support for MPI, so message passing interface. That's often how people write distributed memory code on, say, supercomputers. I'm not going to go into that too much. I'm just going to kind of go through a simple example that just deals with the GPU. But like Nsight Compute, there's many things that Nsight Systems can do that I don't really have time to go over. But similarly to compute, we can use it in this sort of two-phase style where we record data on the target platform using the command line interface and download it to our system and analyze it on the client. So it's similar in that way. And so there's sort of a similar interface for creating application traces. And so this is what you would want to do if you went to the repository and built and downloaded the files. But basically, it's a little bit simpler to use. It sort of does more of the right things that we want by default. So all we tell it to do is the output file and the code we want to run. Part of this is because typically when we're profiling the entire application, we don't care about a specific kernel, right? We need to see the entire execution to understand what the problems are. So there's less of this trying to figure out and tell the Nsight systems what part of our application we care about. Typically, we want to see the whole thing. And so when we open it up in the GUI, just like compute, you can have multiple files up to compare them at the same time. But the main thing that you're going to see sort of in the top right of the screen is a timeline. So time is proceeding from left to right here of the different kinds of activity that are in your application. And so I'm going to zoom in here a little bit. So this is an example. And so this is kind of typical, especially if you're looking at some specific targeted case. So the vast majority of the time in our code is actually spent not measuring the performance of the GPU kernels, but actually just setting up and generating the data that the test kernels will use. So there's all kinds of rows here. Remember, time is proceeding left to right. And so this top part is basically, there's rows associated with every single thread of execution, and Nsight will try to pick out the threads that it thinks are most relevant. It uses a few other threads internally to control the execution of your program and manage some profiling things. So by default, it kind of hides those from you. But this is basically the main CPU thread of execution here, and you can see that it has some capability to measure the CPU load, so that's this kind of top part here, the runtime libraries that the CPU is using, so this has to do with like system calls and things like that. Then this is where those NVTX annotations show up. So I created several annotations in the host code for this example. One of them marks where the data for the profiling is being generated. And so you can see that that shows up here. And most of the time of our program is actually spent generating that data. Then there's the CUDA API calls. And so this is important for understanding, this is the amount of time the CPU spends sort of controlling the GPU. And so this big one here is spent allocating some memory for the GPU. And this is a little bit tricky because probably the first kind of CUDA API call you make, there will be some initialization and startup cost, and so it will appear to be extra long. So this is probably deceptively long, right? If I tried to allocate this much data a second time, it would not take this long. But then sort of the bottom half of this is all of the GPU activity. So you have the kernel activity and the memory activity, which includes getting data to and from the GPU. And so we can zoom in. So we click and drag to zoom in. So I'm zooming in on just the GPU part. And remember at the beginning, I mentioned that when we're profiling often or measuring performance, we'll often run the code multiple times so that we're sure the time has stabilized. And so we can see the sort of repeated pattern of the same thing happening over and over and over again. And so if we zoom into all the way into a single iteration, then the individual operations start to become more clear. So we're doing a matrix multiplication. And on the left-hand side in green, we have two host-to-device mem copies. And then we have the blue, the kernel. And then we have this pink or lavender color, which is the device-to-host mem copy of getting the product back to the host. So we can see this timeline of events sort of executing exactly as we expect. And you can see that I annotated with NVTX the host-to-device and device-to-host ranges in gray. So this Nsight really lets you see a timeline of everything that's going on. And any of these things that you mouse over will tell you more information. So for the mem copies, it will tell you what kind they are and how fast they are. For the kernels, it will tell you what the launch configuration was, so how many blocks and how many threads and so on and so forth. So this is how we can sort of see how the system is utilizing our GPUs. And so you might be wondering, well, how could we speed up this matrix multiplication without thinking about the kernel performance? And to answer that question, we should really think about what kinds of operations we're doing. So I've basically drawn a cartoon of the timeline here. And so the overall time of our matrix multiplication is basically the time it takes to copy the A and B matrices from the CPU to the GPU, plus the time that our kernel takes to execute, plus the time it takes to copy the result back. And so just like in the NVTX timeline, we have time proceeding from left to right here. And the total time is the sum of these three things since they're not overlapped. And so just again, this is that same cartoon zoomed in and blown up really big for you. But we have the host to device time, the kernel time, and the device to host time. And so you can see that in this real life example, this is with the fastest possible implementation that I have. The time that it takes to copy the data back and forth from the GPU is actually about 2/3 of the execution time, and the kernel is basically 1/3 of the execution time. So actually, now that we've optimized the kernel, the limiting amount of the sort of performance limiter for this code is not the GPU kernel anymore, but the fact that we have to get the data to and from the GPU, right? So this is kind of consistent with what Professor Hu probably mentioned about the sort of bottleneck of getting data onto the GPU. So we can see that in this system. But one approach that we could use to actually reduce this end-to-end time is we can recall that we could actually think of this single matrix multiplication as 4 different matrix multiplications. So we can produce 4 quadrants of the product matrix, each of those quadrants from half of the source matrix. So the basic idea here is we're going to want to copy a single slice of A and B onto the GPU, and then immediately start the quarter of the product matrix that uses those 2 slices while we're copying the next slice onto the GPU. And so basically, we're not going to improve the performance of the kernel or improve the performance of the memory transfer, but we're going to improve the overall utilization of the GPU by overlapping the computation with the communication. So once we get A0 and B0 onto the GPU, we can start doing C00, and then at the same time, we can start copying B1 onto the GPU. And then as soon as that's on there, we can compute C01 and so on. And so hopefully what we'll see is something that looks a little more like this execution, where now we can copy these 4 smaller sections from the CPU to the GPU. The total amount of copy time should be the same. And also on the way back from the CPU to the GPU, or from the GPU to the CPU, we can copy the products as soon as they're finished as well. So now instead of having the entire source and product matrix before and after the kernel execution, we managed to overlap half of the source matrix and 3/4 of the product matrix with the kernel computation to improve the overall time. And so if we make that change in the code, on the top is the original one where there's no overlap. And on the bottom, I'm showing the overlapped version. And so you can see we've changed from 2 to 4 mem copies, but we're managing to execute the kernel, these quarters of the kernel at the same time as the smaller memory transfers and overlap them. And in this particular example, we managed to reduce the total end-to-end time by from 3.5 milliseconds to 2.5 milliseconds using this approach. If you look at the code, you'll see that it's quite a bit more elaborate than the baseline code, but these are the sorts of things that you have to think about doing typically to really effectively utilize a GPU if there's substantial data transfer between the CPU and the GPU.
Yeah, so Carl, it may be worth mentioning that the data, there's a kind of a lower bound of data size that you can do it efficient enough data transfer. So we can only divide these things down to so small a chunk.
Right, that's true. And you can actually see that to some degree. I'm trying to think if we really show it, but I'm not really zoomed in here well enough. But basically what you want to think about is in this view, right, we can see these green bars. This is how long it takes it takes the CPU a certain amount of time to invoke these data transfers and control the GPU. And once the data transfer gets small enough, you might spend too much time telling the GPU to do transfer data. And you might spend more time telling the GPU to transfer data than it actually takes the GPU to do it. So you can only, so as Professor Hu is saying, it really only pays off to decompose these things so much. I guess the other thing I would say is that, you sort of have diminishing returns, right? If we can imagine that even if it was big and we decompose this into 3 by 3 instead of 2 by 2, we've already cut off most of the copy time of the product matrix and half of the copy time of the source matrix. So if we make it 3 by 3 instead of 2 by 2, then we're only going to end up cutting off a little more of the source matrix and a little more of the product matrix. And so we sort of get some diminishing returns here. This is kind of like sort of like an Amdahl's law thing. And obviously this is also only beneficial if there is balance between the transfer time and the kernel time. If the kernel time is extremely long, then it matters much less how fast the transfer is. And if the transfer is extremely long, then there's really no point in overlapping it with the kernel. But anyway, these are the kinds of things you can see in systems and figure out how to best utilize the GPU. And so on particular I know this slide is pretty small, so you can download the slides once they're posted, but this has some interesting links for understanding more about Nsight systems and computes and understanding some more about different parts of the workload analysis and stall reasons and how to think about occupancy and things. I would like to tell you that NVIDIA has a one-stop shop online for summarizing all of this information, but unfortunately it's spread across documentation, the CUDA programming guide, the architecture performance guides, the NVIDIA dev blog, and GTC talks. So typically, if you have a specific question, you may have to Google around quite a bit, but between those 5 or 6 places, you can probably find an answer. I often find that an answer to a specific question is in the middle of a talk from the GPU Technology Conference in the past 5 years on some of these architecture performance analysis questions. So it can be a little tricky to track down, but for some further reading, I think these are good places to start. So I just want to end by saying that there are other ways to think about and measure GPU performance that I didn't really discuss. I didn't really talk about how to measure the performance of events, of operations that occur across multiple streams using the CUDA events, but you can do that. Both the Nsight Compute GUI and Systems GUI allow you to run commands and profile them, so you don't have to use the command line interface. I didn't talk about how to do that, but in some cases, maybe that can be easier for you to configure potentially. You can also measure the elapsed time within a kernel in terms of clock cycles using these clock and clock64 device functions. Because of the SIMD execution style in GPUs combined with the latency hiding, trying to have many warps in flight at the same time, these kinds of things can be difficult to interpret, but the ability exists. And sort of the last most sophisticated thing is there's something called the CUDA Performance Tools interface, where you can basically programmatically retrieve at runtime the values of some of these metrics and replay kernels and things like that. So you could basically build your own version of these performance tools if you wanted, or if you just need to record specific things in a way that the performance tools don't give you, you could potentially do that as well. That would be its own multi-lecture thing to describe. But if that sounds like something you're interested in doing, that capability exists. So I hope this has been somewhat useful to you. If not for this class directly, then for your future endeavors. And thank you for your attention. Feel free to take any of this content and do whatever you want with it.
Very good. Any questions? Any additional questions or any new questions for Carl?
The other thing I would say is if you find yourself working on any of this, feel free to shoot me an email and I'm happy to help walk you through some of these questions or look at a code with you or something. I mean, I don't want to commit to helping you out for hours and hours, but I'm certainly happy to help you get started.
Yep. So Carl, The plan is that we will have a simple question at the final exam, then based on some of the material. So I think keep that in mind when you generate the profile data for students to look at.
Okay.
And so, yeah, so that we can potentially have a couple of these what we used to call the study guide kind of questions for 408 that we can give students some practice before the exam. Okay.
Okay, sounds good.
Yep. And so now I definitely want to make a comment here. What Carl presented here is not really available out there, and it is actually going to save you a lot of time. If you're trying to figure out the performance, some of the performance problems, or there may be how to improve, optimize the performance of your GPU code. And so this is really put together by an expert, and so I hope that everyone would be able to benefit from Carl's material.